Hi, this is our senior design project, CLAM, the CisLunar Analysis of Microorganisms. Our goal is to send yeast on a 160-day mission to deep CisLunar space to investigate the effects of radiation on them and to return them safely to the Earth in a groundbreaking, first ever recovery of a CubeSat payload. So, why? Why do this? The point of this is to investigate the exposure of radiation on living things. Space is a massive, growing industry, with stakeholders from NASA to commercial entities like SpaceX and Blue Origin, to the ISS National Lab, and to Georgia Tech, which has many spacecraft on orbit right now. However, the effects of radiation on living things are still relatively poorly understood, but they are a huge threat to anyone traveling to low Earth orbit, the moon, or beyond. We want to help understand this environment by exposing yeast, a organism similar to mammals and humans, to this environment. We want to study both what they experience on orbit by looking at their biological indicators and to study their DNA after they return to Earth to understand what changes this radiation induces and potentially how we can help mitigate or shield against this. We will achieve this using a 12U CubeSat. We will launch as a rideshare. After our deployment, we will detumble, we will orient towards the sun after performing some maneuvers, and we will remain oriented towards the sun for the duration of our mission. This keeps our architecture simple. Overall, our architecture is very simple. There are a lot of components, such as our propulsion system, which have actually been designed in-house at Georgia Tech and have simply been modified for this mission. This means that we can focus on our biological mission. By keeping all of our hardware reliable, we achieve the maximum scientific aims. From the point of view of our payload, their mission starts 2 weeks before our actual launch. They will be dried out, desiccated, and put into their wells before being sealed within the entry vehicle. After launch, they will go through a 2-week checkout phase, which will culminate in them being warmed up and rehydrated with a nutrient-rich medium. Then, they will undergo 4 4-week-long experiments, one for each card. To make sure they get through the very stressful period of entry safely, they will be cooled down to 2 degrees Celsius, where all biological life will cease, but they will not die. They will simply be in a cryptobiotic, near-frozen state. They will also be dried out. They will experience 40 Gs during re-entry, but because they are in this dry state, it is not a risk for them or for the data that they will generate. After their return to Earth, they will be recovered with recovery helicopters and brought to a lab where their DNA can be examined in detail. The yeast genome is fully sequenced, so we're going to have an excellent way to understand the changes undergone by them and their biology. While entry is risky, because an entry capsule this small has never been demonstrated, and we're using an advanced design to keep our payload as cool as we are, this risk is mitigated by the plethora of data that we collect on orbit. We measure the radiation environment the yeast are in directly to ensure that we have an excellent control. We additionally measure their biological vitality by shining light through them and measuring how this changes over the mission. This lets us know how many yeast we have. Finally, we use a dye. The yeast will be dyed, and the way that this dye is changed over time by the yeast metabolic activity will let us know how they're metabolizing. So while we will lose a lot of data if our entry vehicle fails, we still have a backup, and we can still learn from this mission. Let's turn to our systems very quickly. We have an in-house propulsion system designed by Georgia Tech that has been modified for this mission. It previously flew on BioSentinel. Our payload cards are based on a design by BioSentinel, but have been adapted for our mission. We have a redundant attitude control strategy using reaction wheels and the thrusters from the propulsion system. We've got a redundant communication system with 2 sets of antennas. We have multiple ways of determining our orientation using sun sensors and a star tracker. We've got an onboard flight computer that is commercial off the shelf, as is our electrical power system. Overall, this is a very standard CubeSat design, but one that combines existing elements in an innovative way and achieves new heights for CubeSat mission accomplishments. Finally, let's talk cost. We anticipate a $25.9 million cost for a CubeSat, which, while high for a CubeSat, is very low for this level of achievement and is typical for large CubeSats doing large things. I'd like to thank you for taking this time to watch this short video going over our mission, and please, come ask us any questions you have. There's a lot more behind the scenes of this design that we would love to share with you, and a lot more to tell you about the great impacts that this small mission can have.